is Adam Furmanek, and today we will actually talk about why async may be the biggest mistake of C#. And before we move on, a little disclaimer. First, this talk may sound like a rant for you. It may sound like I'm hateful and I don't like this feature at all. It's not the case. The thing is, as with everything we implement, the solutions we deploy, they have some cost with them, associated with them. It may be that this cost is actually overwhelming and outperforms all the benefits. It may be that this cost is pretty diminishable and we can just freely, safely ignore it. And this is what we think about async, that it's free, that it's great, that it's cool. All the tutorials on MSDN side, they just show you put async here, put await there, and bang, you are good. But during this talk, we'll actually learn that, hey, it's not that simple. There are a couple of pitfalls in the mechanism. There are a lot of drawbacks when it comes to the performance. And there are also some principles like decent or best practices, which were broken during in the early design stage. So this is the goal. We'll just research, we'll just explore the async, looking at what could go better, what could be implemented better, and which things are to some extent broken. If you want to get the materials, there is a QR code here, so you can actually access the materials directly. Also, you can just go to my blog at blog.adamfurmanek.pl, and then you'll find the talk, Async Biggest C# Mistake, and you can find slides over there. When it comes to questions, as it was mentioned, I will try to answer all of them posted in chat after this talk. That's because I have just one screen for today, so it's hard for me to keep the track of all the questions you may be posting. But if you would like to get something answered immediately, feel free to speak up. Also, it was said that this talk will take around an hour. It may actually take a little longer because we have plenty of time. So I will try not to rush today, and I will try to explain all the things down to a single detail, but do it a little slower than typically. Feel free to drop me a line on Twitter or email if it works for you after this talk, if you had any questions, which I will not, or I may just not cover during this talk. Okay, let's move on. Before we actually get to the async stuff, a couple words about me. I'm a software engineer, experienced with .NET for like 5 years, currently working at Amazon with machine learning, big data, all that fancy stuff. Blogger, public speaker, author of .NET Internals Cookbook. Please feel free to take a look if you're interested in the internals. Drop me a line on whatever social media you enjoy, and I encourage you to take a look at my blog. Agenda for this talk. So we'll go through a couple of issues, couple of problems associated or appearing with when using async and await. So we'll go through a couple big areas where it could be done better. So the first area is we'll see that it's expensive and that it's not free, that it's very expensive when we are using it a lot. And this issue is actually increasing more and more over these days because, hey, a couple of years back, we had async only in couple of APIs, but right now almost everything is async enabled or awaited. So this cost is increasing significantly. Like one day we may get something like console.writeLine async. It won't be that much surprising, but this thing will be actually only increasing the cost we need to pay. Then we'll go through a couple of different principles, which we generally know we should be not breaking, like we should not be using hidden state, should not be using global variables. We should integrate with platform well and write the idiomatic code. And we'll see how all these things were basically broken when implementing async and await. And at the very end, if we have some time left, we'll actually see how to make things better, like a conceptual approach. But I do want to warn you that I do have a completely separate talk covering how to re-implement async in a better way. So it will be just a sneak peek of what could be improved. Okay. Let's go. So the first thing is it's expensive. When it comes to the async method, if you ever seen my talk about internals of async, we start with this method and I go through all the nifty-50 details of the async method, how it's compiled. So I won't be going through this today. I just want to give you some intuition how expensive the asynchronous method may be. So when we start with a method like this, in which we can see that we just have 4 different logic logical part separate with await keywords, this code is initially this code is then compiled to something which, well, starts with much more complex, much more convoluted code. That's first thing. But second thing, if we actually see how long this code becomes, after decompiling, we can see that this one single method was compiled to something like 130 lines of code. And we can see multiple variables here. We can see some hidden methods. We can see some helper methods like magical constants. It's all implemented, all generated for you by the C# compiler, and done behind the scenes for you. So this is to actually enable the whole async await machinery. And it looks great because, hey, we don't need to think about that. But once we start revisiting these things, we realize that the task thing is allocated on the heap. And if it's allocated on the heap, it needs to be collected by the garbage collector. And because it needs to be collected, it takes time. It takes additional memory, which we need to reclaim at some point. And generally, because it's GC, we also need to stop the world, stop the threads, and do all the magic things just to free that memory. To help that, Microsoft realized, or people at Microsoft realized that we need to have something better. So they introduced a value task, which is basically just like a task, but it's not heap allocated. It's structure, so it's stack allocated and does not need to be reclaimed by the garbage collector. However, using value task is actually not necessarily a solution for all our problems. I will see later on, but if you would like to see how to improve at least this one single aspect of the async machinery, feel free to take a look at Pooled Value Task Source by Konrad Kokosa on GitHub. And I also really encourage you to take a look at Midori blog post series by Joe Duffy, where he explains how the whole operating system was implemented with the async API, which was based on the value tasks under the hood. But I mentioned that it's expensive. If you actually go to the Microsoft official sources, if you go and try to figure out how expensive it is, you can read that each await operation for an unfinished task may consume a couple hundreds of bytes. That depends obviously on the thing you are waiting on. If it's like a generic task, if it's a non-generic task, etc., depends on the platform, whether you are 32-bit or 64-bit. But generally, the thing is, with every single await, we spend a couple of microseconds, and also we allocate sometimes a couple hundreds of bytes. Which is a lot, because with the async and await operators in place right now, all our APIs, they are basically async enabled, so they may consume a lot of memory, a lot. Even if we use value tasks, they can remove some overhead, but they won't remove the overhead if we actually need to wait for these tasks to finish. So this is something which will be increasing a lot over the next years once everything transitions to async API. So this is the cost we will always have in the C# language. It doesn't seem like we could ever get rid of this cost. It may be that this cost, it's likely that this cost will stay with us like forever. So we'll increase the memory. And because the task was initially implemented as a heap object, meaning it's a class, not a structure, this means that we'll practically never get rid of this allocation, of this whole cost which is associated with this GC tracking. So this is something we should keep in mind, and sometimes we should ask the question, hey, is it actually good to make method async enabled, or maybe we should just go with returning the task directly to avoid this allocation? But this is just the beginning. Now let's go and see how it uses hidden state. And this is very tricky because it may cause deadlocks in our code base pretty easily depending on what we are doing. The thing which we typically ignore when talking about async and await is like we go to MSDN tutorial, they tell us, hey, put async here, put await there, bam, you're done, you are good, everything should work. But they typically omit this fact that behind this whole machinery, there is a thing called synchronization context. This thing is basically a bag for logical execution of the code, because we do have this await operator and we do have all these continuations after we finish waiting. They need to execute and they need to behave just like the regular code we have written, meaning they need to have the same permissions, they need to have the same impersonation context, the same user. We probably think they should have the same thread local variables, and all the other stuff which we take for granted and we don't want to handle explicitly manually. All these things should just flow freely between the executions. And this is what synchronization context does for us. It synchronizes, not necessarily in the sense of using synchronization primitives, but it makes the whole context of the execution to flow with the continuations we execute. And the thing is, depending on the type of application we run, we may actually end up with the same code working in one of type of the applications, but break or actually deadlock in some other place. That is because depending on what synchronization context we have, we get completely different scheduling experience, completely different behavior when it comes to the scheduling and orchestrating all these continuations. So depending on the type of application, we get, for instance, different number of threads executing the awaited continuations. If we are talking about desktop applications, this includes like old things, for instance, WinForms and WPF, but this also includes things like, for instance, Xamarin or Blazor, because they do have the concept of the UI thread. In these applications, the thing we have is there is one thread which is designated to be allowed to modify the UI controls. It's so-called the UI thread. So whenever you await something on the UI thread, you effectively require that the continuation continues on the same UI thread. So if you block the thread by calling .wait, .result, or doing something else, you actually block the application permanently because continuation cannot be scheduled on the thread. Similar thing actually happens, for instance, in ASP.NET applications, because there what you have is not necessarily the UI, but the request context. You would like to flow with your continuations. So you would like to have the HTTP context, the request details, go with your code as it executes after being awaited. So in that applications in ASP.NET, it means that whenever you do have a continuation, only one continuation in given HTTP request can be executed at given moment. This means that if you await multiple tasks, they will be linearized. They will be executed one by one serially because only one continuation can run within a given web context. This was changed around ASP.NET Core because this means in ASP.NET Core, we do not have the synchronization context anymore. So if you, for instance, migrate all applications to new ASP.NET Core, you actually get parallelism, which wasn't there initially. So you may actually break your application accidentally due to that. So it depends on the type of application you execute. And if there is no synchronization context explicitly specified, we use the default thread pool-based logic, which gets your continuations and executes them on the thread pool, the static thread pool, which is available in .NET. And that thread pool contains multiple threads. So if you start executing multiple continuations, you may actually basically schedule too many things. So your thread pool explodes, creates too many threads to execute the things for you, and then you basically exhaust all your resources of the machine you are running on. So to give you a little more understanding of how this works, I will start with this basic principle. If there was one slide you wanted to remember from this talk, it's this one, and it tells you to use async all the way up and use configure await false all the way down, and never wait for tasks synchronously by calling .wait or .result or whatever else, because it will just break your application sooner or later. So let's now see how it breaks these applications and how it works. In order to understand what we can do, we need to see how the synchronization context can be controlled and what does it mean for the continuation to actually be executed. So we start with this code in here, and what we do in this line, you can see that we are calling await, but we are not doing the configure await false in this line. This means that the synchronization context is captured in this application, and this application, as we can judge by the signature of the function is probably some desktop application or some application which has UI-based synchronization context. Could be Blazor, could be something similar. So what happens now is once this process data async finishes, this part of the code must be scheduled as a continuation to be executed. So this part we call the continuation. And because we didn't ask for configure await false, it means that this continuation here is going to be executed on the synchronization context tied to this thread. So it will be executed on the UI thread. But if you do understand how these things work, we actually know that when calling this method, we execute it synchronously. So we do not do any like context switch or whatever else. Just in this line, we go directly to this method and start executing it. So in this method, we do something similar. We call await download async and we ask configure await false, meaning that, hey, do not capture the synchronization context which is there. So what we do now is we get this continuation, and this continuation here is going to be executed on the synchronization context. And because we did not capture the synchronization context, what is happening actually now is this thing, if awaited, will be executed on a thread pool. This means that because we never know if this thing is going to block, because hey, it could be that it executed on the for instance synchronously because it was filled from the cache or something like this. But then the continuation, if it was awaited, will be executed on the thread pool. If we had to await, if we didn't have to await, we'll just carry on, continue on the UI thread. So then we can generally assume that if we did a network call, we had to download the data like for real. This thing is being executed on the thread pool thread, not on the UI thread. So it means that here at this point, we are on the UI thread. Here in this line, we are on the UI thread because we trigger the operation from the same thread. But then here in this line, we are actually executing on the thread pool thread. But then we come back to this line here, and because we didn't ask for configure await false, this whole continuation here is going to be executed on the UI thread. So this thing is on the UI thread again. So this is how synchronization context is passed between the threads, how it flows in the application. And depending on what type of synchronization context we have, we may actually end up with deadlock, which would not happen in different type of the application. So what we are going to do now is we'll understand a couple of applications and see why they work and why they break. So what we do here is, let's take this code. This is a console application. So what we do here is we trigger operation on context. And at this point here, we do not ask for the configure await false, meaning that this continuation is going to be executed on the synchronization context which we captured. And because this is a console application, then the whole machinery under the hood goes to the thread pool. So even though the original thread where we started is blocked because it calls the synchronous.wait operation, this part here, this continuation here, has another thread in the thread pool which it can use to finish the execution. So ultimately, this continuation here finishes on the thread pool, and then this original thread gets unblocked because, hey, it executed, it finished waiting for the continuation, so it worked. However, if we go to the user application, like user interface application, like desktop, WinForms, or whatever else, what happens is we actually end up with completely different behavior because we start on the UI thread and we wait synchronously, so we block the UI thread. What is happening now at this point, we do capture the synchronization context. And because we capture it, this continuation wants to execute on the synchronization context which it did capture. And what it captured is the desktop synchronization context, which goes to the UI thread. So this line here does not have a thread which it could use to execute because the original thread is stuck in this .wait operation. This means that we literally took a code from the .NET console application, moved it to the desktop application, and bam, it stopped working because now we have a deadlock. What can we do with that? Well, the solution seems to be pretty simple because we understand that, hey, the solution is to add the configure await false, because once we do this, the continuation, which is here, does not execute on the UI thread anymore. So even though this thread is stuck, your user interface, your desktop application is basically frozen for a second because we are sleeping for a second. Ultimately, the continuation here finishes on some other thread, and we can unblock the application after a second. It's a terrible user experience, but at least it works. We can recover. But hey, is it like, it seems like, okay, so never capture the synchronization context, always use configure await false, and it seems like it's going to work, right? Well, and not necessarily, it's not that simple. That is because if we explicitly ask to go to the UI thread, we end up with the same deadlock, because what we do here now in this code is this continuation here is being executed on the thread pool thread because we asked for configure await false. But what we do here is we explicitly ask, hey, please take this lambda which does messagebox.show and please run it on the UI thread. And what does the UI thread do? Well, it's stuck in .wait operation. So it's basically deadlocking again. So you can see that, that the same code, it didn't work this time, because we explicitly asked to go to the UI thread. Is there a solution for this thing? Well, there is one, which is a bit hacky, but maybe it will be useful for some of you. Hopefully not, but well, you know how it goes. Instead of calling .wait, what you can do, for instance, in WinForms application is you can always ask the application, hey, do you have anything which you would like to execute on the UI thread? And the synchronization in WinForms is performed, and in some other applications as well, like WPF, like Blazor, etc. It's always based on this principle. There is a queue, message queue, which holds the code to be executed, and which we need to periodically explicitly check. This is something which the framework does for us, but we can always explicitly ask, hey, please take the queue, go through all the messages, try running them if that's possible. So this is what we do here. Instead of waiting like with .wait, we basically wait for 1 millisecond. So we spin loop, spin wait, and then we ask the application, hey, please run all these events for me. So even though this continuation goes to the thread pool, we ask explicitly, hey, please execute this lambda here on the UI thread. So this basically sends a message to the queue, which we explicitly handle here while being on the UI thread. So this is how we can fix this, how we can work things around, but generally this is a hacky thingy. And the thing with synchronization context is that it is relatively easy, relatively simple to forget about that, to omit a line which we need to cover with all this logic of capturing or not capturing the synchronization context. And I told you with this slide with big red font telling you async all the way up. So you never need to call .wait because you can just await the code, but also told you to do configure await false all the way down. And what does it mean and why it's important? That is because if we take this code here, what we are doing is we start with very similar logic at the very top. Hey, just run this task for me, and then getAwaiter.getResult is almost equivalent of .wait or .result, etc., etc. This doesn't matter how it works under the hood. It just changes a couple things of exceptions, etc. But you could put .wait here and it would be the same. So what we do then is in the wait1 method, we call wait2 and we configure await false. So this continuation here will not be executed on the UI thread. Wait2, on the other hand, calls wait3 and doesn't ask for configure await false. So you can see that it would like to execute on the UI thread, but with wait3, we again ask the continuation to not execute on the UI thread. So you may think, okay, it should work because, hey, at the very top, I asked for not running on the UI thread. At the very bottom, I asked for the same, but in fact, it deadlocks again. Why is that? Because here, once this continuation here finishes, we are not on the UI thread anymore, but we come back to this place in wait2. And because wait2 explicitly or sorry, it didn't explicitly ask to not capture the synchronization context. It captured one which was available there. So we tried to go to the UI thread again, and the UI thread is stuck in here. So this is how we can flow the data between the threads, and we explicitly need to ask for configure await false in every single place. Otherwise, we get the deadlock again. So configure await false all the way down and async all the way up. And I told you that this thing uses the hidden state. So what is the hidden state here may be actually very tricky because, well, it's hidden. We do not see the state. Let's take this unit test. Obviously, we never write unit tests with like accessing WinForms controls or whatever else, but hey, sometimes it just happens, right? So we take this test. And what we do is we create a new form from WinForms framework. We wait for 1 second, and then we just say, hey, the test succeeded. What happens with this test is it never finishes. It deadlocks again. Why is it possible? That is because what happens under the hood is when we call the new form of the WinForms, the chain of constructors initializes the framework. So at some point it goes and asks, hey, what is my current synchronization context? And because any unit uses different synchronization context, it steps in, WinForms steps in and just replaces the synchronization context for you. So the end unit waits on different context than the WinForms framework, so you basically get a deadlock. How can we fix that? Well, yet another hacky solution. We can get the current synchronization context, which is a global variable, and we can replace it later on the thread. So at this point in this new form, this synchronization context is basically removed and new context is created, which is backing the WinForms framework. But later, we can restore this context so we get the original behavior back, and then this assert pass finishes successfully. So this is why async and await is very tricky, because it uses these global variables, which we first may not be aware of. Second, anyone can just step in and replace for us. And third, depending on the application we run our code in, we get completely different behavior, and we cannot rely or we cannot have assumptions what the behavior will be because we don't know what the synchronization context is. So this is basically one of the biggest points or issues with async and await. And these issues are basically, it's easy to deadlock. It's easy to get our application stuck. So async all the way up and configure await false all the way down. Never wait synchronously on the tasks because otherwise you risk a deadlock. Moving on to another area is it doesn't integrate with the platform well. And we'll see a couple of examples where async and await just don't work with the rest of the C# language, which is there for a very long time. So the first thing is like how we handle exceptions. When it comes to using the async and await, what we use under the hood is the task class. And we know that the task class is basically tied to the TPL, task parallel library, which was there a couple years back before the even async and await emerged. So there is quite a lot of code which is using the task object or the task instance like the same way seemingly to run asynchronous operations, but it's doing something completely different because it's using it in the TPL world. So what can happen is in TPL, we can not only create tasks which are executed like one by one, so awaited linearly or serially, but we can also create a tree of tasks. And if an exception is being thrown in the tree of tasks, we get the aggregate exception. So let's now see what is happening if we are getting the aggregate exception with the code which we are running with async and await. So what we do is here at the very bottom, we basically start new task, and then we create two different tasks. We attach them to parent, so we created a tree of the tasks. So these tasks are not like executed linearly. It's not a straight line. It's a tree basically of the tasks, and we throw two exceptions. What we do then is we just await. Okay, let's await this task. So we await this whole big task here at the very bottom, which has 2 exceptions now. But what we get in the output is basically only one of the exceptions. Not only we miss one exception, but we also don't know which one is going to be presented. So the other exception is completely lost, and we don't even know which one it was. So what we can do, or actually what we need to do in order to fix this behavior, is we need to go back to the, and sorry, my screen just got stuck because of the Zoom. Okay, what we need to do is, we are back. What we need to do now is we cannot use await anymore. What we need to do is we create the same tasks as before, but instead of awaiting them, we basically need to create continuations with the continue with method, and then the continuation, like which run on completion or which one on run on faulted, can actually capture both of the exceptions here. So you can see on the right side of the screen that we have both of the exceptions captured now, the second task exception and first task exception. So this is what we need to do in order to handle the exceptions correctly, and await just doesn't match in this world. If you use TPL, and there's quite a lot of code using TPL, this is where we need to use we cannot go with await anymore. But it's only the beginning of the story of exceptions. The other part is how we throw exceptions in async void and async task methods. Obviously, we should never use async void methods, but generally sometimes we do because framework requires or expects that from us. So what we need to do is we need to be aware of the fact that the exceptions in async void and async task methods are handled completely differently. So let's actually move on to some code, and let's start some application here. So what we do is we do have a main method, and in this main method, we call method throw twice and try catch on these invocations. Method throw is async void method, which waits for 300 milliseconds and then just throws the exception, okay? And then after this try catch block, what we do is we print something, we sleep, and we print something again. Let's run this application and see what is happening. So you can see, what you can see is that we did execute the code, the application, and you can see that all the lines were executed, were printed out. So it seems like the application finished, even though we did have this unhandled exception printed out, okay? So it seems like everything worked, but it's only like a false positive situation. Because if we now add the thread sleep, imagine that we think, okay, so this thing waited for 300 milliseconds. So maybe let's wait 5 times longer, and then this exception, which is thrown from here, maybe we'll just capture it with try catch. So let's see, let's run this application now and observe that like when we run this application, it not only crashes, but also so the exception handling machinery didn't work. But if we even continue with it, you can see that this done line wasn't executed at all. So we introduced like a random sleep, random delay somewhere on the chain of execution, and we basically changed the behavior of the application. We changed significantly because previously it did succeed. Now it crashes significantly and it just doesn't work. So this is what happens with the async void methods, and the fact is never use async void methods. But if we run async task methods, it's only a little better. First, Visual Studio tells us, hey, we are not awaiting this throw, which is important. We should always await the tasks which are returned, because if we do not await them, what you can see is, yes, the application did succeed, but hey, the exception was lost. So we don't want to lose the exceptions. And here comes the yet another principle, or actually 2 principles. First, never use async void methods. And second, always await all your tasks. Otherwise, you lose the exceptions and it may just break the application for you. Okay, moving on. So this is how exceptions are handled in the application. And I mentioned that we've seen that first, await async void methods, they do break the application because they throw this exception. And the issue with async void is we just cannot await these methods, or can we? And I'm going to show you how we can await async void methods. And in order to do that, we can actually reuse the machinery which we already have under the hood, which is called, let me just start the correct project. So what we are going to do is we are going to re-implement the synchronization context and the task scheduler. So let's go at the very bottom. We do have the method called throw, and this method just waits for 1 second and then throws the exception, okay? And it's async void. So we cannot await it because it doesn't return the task for us, which we could use. But what we can do instead is we can first create our custom task scheduler. This task scheduler is going to basically queue task for us. And then we create our custom synchronization context, which uses our custom scheduler and uses custom task factory, which hides the original scheduler and uses our custom one instead. And this synchronization context is capable of calculating the operations, how many of them are in flight, how many of them are started and haven't finished yet. And what we can do is we can provide a very simple method, which will just create a new task, replace the synchronization context on the task, or actually on the thread, and then iterate through all the tasks which were created inside this given synchronization context and execute them one by one using the for each loop and await them, or actually synchronously wait them explicitly. So what happens now is, instead of calling this throw method like directly, we can just use this helper method from the context to create this lambda and to run this method. And then we get a task. And once we have this task, we can call get await or get result, or wait or result, or just await, or do whatever else. And this exception thrown here in the async void method is going to be handled by this catch handler, okay? So we can see the output of this application that not only we, oh, sorry for that, not only we did print out the output of this application, so not only we presented the swallowing exception, which is somewhere here, but also we succeeded and the application did not crash. So this is what we can actually do. And in fact, we can await async void methods, but it gets a little more tricky, a little trickier than typically. Okay. So this is the thing which we're probably aware of. There are a couple more things when it comes to async void, because async void is not necessarily about returning void from the method. Async void is about not being able to return task. And there is one more place where we cannot return task from the method, and it's basically a constructor, because constructor needs to return the instance of the type it's creating. So we cannot make the constructor async enabled. What we need to do instead is we need to use the so-called async constructor pattern, which you can see on the right. So we are creating a new instance with like the default constructor, and then calling async enabled method called initialize async. And the constructor is private, it's not exposed. The thing is, first, it's logically equivalent to what we want to do, but it's only blocked by the language and the machinery under the hood. And second, quite a lot of mechanisms, they do rely on the async, on the constructors, which should be available for the application, or sorry, for the type. So it means that, for instance, activator create instance, or some deserializers like JSON deserializer, XML deserializer, etc. They may expect, or they may require that we use the constructor of the type, not some async constructor pattern, which is not idiomatic. So in that case, we are basically going against how the application should work. And why would we ever need, or why would we ever want to use the async enabled method inside the constructor? And one of the popular use cases is when you are doing the domain-driven design applications, for instance, you sometimes may want to call service from your constructor to guarantee that, hey, I don't know, an email is unique. So you need to go to the database and basically query it from inside of your constructor. Some people do implement it this way. And in that case, you cannot use the async API from within the constructor. But it's not generally about the IO operations. It's about this whole approach with coroutines, with call CC, with other things which do rewrite the application, which do rewrite your methods. And the constructor just like doesn't fit. It doesn't go well, doesn't align. So this is another place where async and await do not integrate with the platform well. But there is yet another one, which is called locking. If you ever tried doing await inside the lock construct, you probably noticed that compiler prevents that, stops you from doing that because, hey, await cannot be used inside the lock. Why is that? That is because if we understand what's going on under the hood, we know that this thingy here does not necessarily need to execute on the same thread where we started, because we start on one thread and then this continuation may execute somewhere else, for instance, in console application, or we could even do the configure await false here, and then we would just go to the thread pool or whatever else. And because locks are always thread-based, it means that this thingy here, this lock here, ties the ownership of the synchronization primitive to the thread we are executing on. So if we switch threads, at this point, we do not hold the lock anymore, even though we are in the same part of the code. So compiler stops us from doing that, but hey, we may be a little smarter. How about unrolling this piece of code like manually? We know that the lock construct is implemented as monitor enter, so we can write this code by hand and it does compile. But it's not only about locks and monitors. Imagine you use some system-wide synchronization primitives like mutexes, like semaphores, which are provided to you by WinAPI and like wrapped by the .NET API. In these situations, you don't use lock. You need to explicitly call like lock on the object or try enter on the mutex, and then you need to release it explicitly. But what happens once you do that? Well, because this continuation here switches threads, it moves to different thread number 4, while previously we were on the thread number 1, we get this exception that, hey, we tried to like release the object from unsynchronized block of code. So we just break the application. So the outcome of this whole async await machinery is you cannot use the regular synchronization primitives anymore. You need to move on to completely new async enabled primitives because the regular ones, they just don't work with this approach anymore. And this is yet another place where it doesn't integrate with the platform. And this concludes this part. And now we'll actually see how it breaks the decent programming principles. So we already seen a couple of them, like things like we need to call configure await and other things. We would like to use constructors, but we cannot anymore. But hey, there are actually much bigger principles which are very hard to be applied, which we cannot apply easily in this piece of code with async and await, or which were broken in the design phase. So first thing, when it comes to any synchronization code, any parallelism, any concurrency, is never wait without a timeout. If you ever wait without a timeout, so you wait indefinitely, sooner or later you will get a deadlock. Never do this because it will kick you one day. Always set a timeout which may seem ridiculous to you, like ridiculously high, for instance, an hour of a timeout, and one day you will be just surprised that, hey, this timeout was hit. So how do you await with a timeout using async and await? And to do so, we'll actually go and see some source code again in Visual Studio. So what we are doing is we start with this very simple method which hangs, and hang here means that we just like wait for 1 minute. Imagine that 1 minute here means indefinitely, okay? And we do have this helper method which waits for a second. 1 second is our timeout, and then throws the exception. So we would like to tie these methods together. So if this method hang does not finish in 1 second, then here after waiting for 1 second, we basically throw the exception or just break this, like exit this, stop this waiting. So the code which we can like write, which we typically write, is we need to do task when any and trigger both of these operations together. So we use this method to trigger both of these tasks at the same time, and task when any gives us the task which finished earlier, so the first task to finish. And in our case, it's going to be this task because it waited for a second and then thrown the exception. And again, what we need to do is we do configure await, we await this thing, we get the task, we configure await the task, and we do await again. And bang, this ultimately, this task is going to be awaited here in the line 10, and it will just throw the exception on us, or it could do whatever else, but it means that we'll just stop waiting. Obviously, we could also cancel this task. So there are a couple more things which we should be doing here. This code gets even more complex, but I'm not necessarily focusing on this part. But you can generally see whenever you do await on some task, you should actually be writing code like this. Never wait without a timeout, never wait indefinitely. So obviously this looks bad. Can we improve this code a little? Well, we can. We can, for instance, introduce the extension method. And yes, extension method is relatively straightforward. We just do the same thing which we did previously. We start the task, we start the timeouting task, we await this with configure await false, then configure await false again, await again, and bang, we end up with this very simple line. So if you ever went to MSD and tutorial, it told you, hey, just put await here, while in fact it should tell you, hey, just put await here, just call configure await false here, just call timeout here, and probably you may have like one method to like generic method to handle all the exceptions in a uniform manner. So you could probably end up with something await yada yada dot timeout dot handle exceptions dot configure await false. So this is how your whole code base should look like, how you should transform every single await line inside your application. Obviously, it's not nice. But actually, this is the best solution, at least in my opinion. Obviously, this is a matter of taste, but I don't think I'll show you a couple other solutions, but I'm not necessarily sure they are better. So this extension method is generally the well-accepted approach to this issue. But we could do something else. We could, for instance, use the synchronization context, right? We already know how to implement the synchronization context. So again, we create the task scheduler, we create the synchronization context, and this synchronization context, when we run something, it runs another task on the side and then calls dot set exception on the original task and does this whole magic and continues with etc. etc. So the execution at the very end looks like this. Instead of calling the hang method directly, we wrap it inside the synchronization context, and then at the very end we just configure it false. In my opinion, it's not better. That is because we need to wrap it inside the synchronization context, not to mention that it's even more allocation. So this is probably not the best solution, but conceptually, well, it's doable. This is something we can do. There is yet another solution which seems to be very clean. On the other hand, it has one drawback. So what we can do is we can create a custom task type. Just like we have a task in our code base, just like we have a value task in our code base, we can create a custom task called timeout table task. And this timeout table task needs to use the builder. So this is a piece of machinery which sits on the side and handles the construction, the orchestration of the task. And inside the start method, what we can do is we can trigger this the side task, which will time out after a second, and we'll just continue with set the exception, etc., etc. So notice that now this line looks clean. We just call hang method with configure false, but we need to return the timeout table task from this method. This means that once you interoperate with any API which is there, which uses the task hard code type, well, it doesn't work anymore because you changed the task type. So while it would work nicely in your code base, once you cross the boundary between your code base and some .NET API or some other external world, it just doesn't fit, doesn't go well anymore. So as I mentioned, probably this timeout with extension is the best solution you can get once you hide this method somewhere deep inside your utils, classes, or whatever else. It's not that bad, and it can handle quite a lot of these. So, so this is how we can do this. But the thing to remember is you cannot just do it with await. You need to write some of your code, a piece of your code. You need to trigger another task on the side, which increases the allocation. So you have plenty of things which you unfortunately need to deal with in order to do it properly. So this is how we await with async, and we can skip these slides. Yet another principle which is broken when talking about async and await, is the principle of do not repeat yourself. So here you have a method internal read all text, which is basically code when you call something like file read all text. Okay, so we want to read whole text of the file, like whole file into memory, and that under the hood, it goes to internal read all text, just creates a stream reader and returns you the stream reader, hey, read to end. And this is from .NET source code, so you can find this code on GitHub or wherever else. But this is for synchronous method. What if we wanted to do read all text asynchronously? Well, and then we actually get to code like this, which is not the same code. You cannot just call synchronous method from asynchronous one or the other way around. You cannot call asynchronous method from synchronous one because you risk deadlocks. You need to re-implement the whole logic twice. You need to do it for synchronous part and for asynchronous part. And you can see that the implementation for asynchronous part is not trivial. It's not that you just call stream reader and hey, read to end. No, you need to start buffering, you need to do the cancellation tokens, you need to do plenty of other things. So when it tells you what I mean by do not repeat yourself is you cannot now just write your piece of logic, like your business logic, and use it both in synchronous and in asynchronous contexts. You need to re-implement this logic twice to actually suit both of these use cases. And because we are still in some sort of transition period from whole API being synchronous to whole API being asynchronous, we cannot, unfortunately, we cannot just go with one implementation. We need to provide two. So do not repeat yourself is broken with this async and await thingy. But then we get to the much bigger principle, which was broken, which is broken, and it's called dependency inversion. And before actually getting to why it's broken for async and await, I want to explain a little bit more of the fact that dependency inversion is broken throughout the whole .NET platform, throughout the whole C# language, because it's very simple to break this principle, and it's very hard actually to fix it now. Before getting to await, let's see how dependency inversion principle was broken with string types. So what the principle tells us is we should not code against concrete implementations, but we should code against the abstractions, the interfaces we can think of. But when we use strings in C# language, the string is, hey, it's a class. It's system.string class, which is a concrete implementation, very specific one. So how do we replace system.string with our custom system.myCustomString? And before getting to how to do that, we can ask a different question. Hey, why would I ever want to replace system.string? And this is a very good question, and the answer is very tricky. It does happen to improve performance. When we take a look at Java language, initially Java and C#, well, first, they are clones of each other, or mostly C# is a clone of Java, at least in the early days. So it took a lot of principles or a lot of like technical designs from the Java platform itself. And Java implemented strings as an array of characters under the hood. Each character is 2 bytes long, so it's 16 bits. That is because we wanted to, or Java wanted to store a little more characters, or actually wanted to cover whole Unicode at the time. Unfortunately, it doesn't apply anymore because Unicode is now much bigger. So it doesn't fit in 2 bytes or in 2 octets. But because most of the texts we are storing in our application are ASCII texts, right? So we don't need to have 2 bytes per each character. 1 byte is enough. So this is what Java 9 introduced, or in JVM in Java 9, they wanted to change the implementation to store strings as bytes instead of as characters. And they decreased the memory usage very significantly, and obviously improved the performance as well, for not for all the operations, but for some of them. And this is something which we would like to do in C# as well, right? But hey, how can we replace system.string from characters to bytes? There are also other things, for instance, concatenation performance. Before Java 9, the Java compiler was compiling like string plus some other string, the plus operator in between. It was compiling it to systembuilder.append invocation. However, starting in Java 9, they changed this solution to the invoke dynamic opcode under the hood. So when you start your application, the first time you hit the plus operator in between strings to concatenate them, system, what happens is this invoke dynamic generates a piece of code for you, which is then used later with full speed. And this piece of code does the concatenation in the most efficient available way, meaning that the same plus operator is not hard-coded anymore to string builder, but can be generated and can be improved over the years when the runtime platform changes. So this is what happened in Java to improve the string performance. Similar thing actually happened at Facebook. There is a cool talk which is called The Strange Details of STD String at Facebook by Niklas Ormrod, which I recommend for you to take a look at. And it explains how they implemented their own string type in the Facebook, which resulted in decreased memory usage by 1%. You may think that it's not much, like 1%, how much is that? But in fact, when you think about Facebook scale, you realize that, hey, 1% may amount into thousands of machines because, hey, Facebook is relatively big. So 1% performance or memory gain is a lot. It's like something which can actually measure in US dollars or in any other currency, but it's a real money which we get just by replacing the string. So again, we may want to replace system.string in C# to increase this thingy. And the last thing which we are going to cover from other platforms is what happens in V8 in the JavaScript runtime in Google Chrome browser. So what they do over there is, depending on how we access the objects, these objects are stored under the hood differently. If we are using array, that they are like allocating objects differently than when we are using them as hash maps, or when we are using them as, you know, prototyped inheritance-based objects or something like this. So depending on the use case, the V8 engine recognizes what we may want to do with these objects and allocates them differently. This is yet another thing which we would like to do under the hood, which we would like to change inside the basics of our platform. But in order to do so, we need to have this fuse to be able to enter this logic. So coming back to C# and to the dependency inversion, how do we replace a string in C#? Well, we cannot, because string is a class. So here is where the dependency inversion is broken, because we code against a class instead of against an abstraction. Second, it's a sealed class, so we cannot inherit from it and use polymorphism to do some magic. Third, it's exposed on the intermediate language level. So when you go to the C# or .NET bytecode, you can see that all the literal strings which are encoded there are basically compiled to the system.string literals under the hood. So it's super coupled with the type which is there in the platform. Not to mention that it's coupled with the actual execution engine, because it relies on the actual memory layout of the string. So to start our digression like about the dependency inversion, we need to understand that dependency inversion is broken throughout the whole C# language, but it's broken inside async as well. And to understand why it's broken, let's consider one more thingy before getting to await. Imagine that you do have a language. You are learning a language which tells you that, hey, you have two different types of functions in your language. Each function has a color associated with it. And so the function can be either green or red. Okay. And the thing is, when you have these two methods, like you can call green method from another green method, you can call red method from another red method, you sort of can call green method from red method, even though it may be dangerous, but you should never ever call red method from inside of the green method. So imagine that you are learning language like this. And what do you think about this language? Hey, you may think, that's some trickery going on here. Why do I have two different colors of methods? And this is actually what is happening in C# now, because your green methods are synchronous methods and your red methods are asynchronous methods. And I told you, you should never wait on the asynchronous method with .wait or .result, because you risk deadlocks. So how do you call asynchronous method from a synchronous one? Well, the answer is you cannot. You cannot call asynchronous method from the sync counterpart, because you cannot await this method. In order to await the method, you would need to change your synchronous method into the async enabled one. The same goes actually the opposite. You can call synchronous method from asynchronous one, but it's tricky because, hey, we are losing all the benefits of async and await. But it gets even trickier because it actually in C# with the value tasks, we have now three colors of our methods. We have now synchronous method, we have value tasks method, and we have regular task method. And depending on where you call them, it may be either like very, very dangerous because you risk deadlocks, or it may just impact the performance. So this is where we start. This is why dependency inversion was broken, because we rely on multiple things of the implementation under the hood, and we just cannot write the code blatantly without thinking about the internals. And now let's make it better. Let's see if we can improve the code just a bit. So what we are going to do now is we are going to quickly see if it's possible to re-implement async a little bit better. And as I mentioned, this is a sneak peek of my other talk, so forgive me for not going into details a lot, but we are already out of time. So let's spend a couple more minutes on that to see if it works and how it can work. Okay. So what we are doing is we are calling a regular async method. And in this regular async method, what we do is we run two different tasks. One of them is called run internal. The other task is called side job. Run internal is just to present how the asynchronous part of not blocking the thread works. So what we do is we call from run internal, we call nested method, and notice that we await it only here. But in this nested method, we call the task delay and we await this delay here. And then we carry on, we extract some data, yada, yada. And in side job, what we do is we just print. So if you understand how these things work is we first call this synchronous method, this asynchronous method, but we call it in a synchronous manner. So we start executing it and we get through this run internal to run internal nested, we get the task delay, and ultimately we just await here. Now because this delay hasn't finished because we are waiting for 2 seconds, we unroll ourselves. So we go up, 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 and we get to the side job. And now this side job method gets a chance to be executed. So we go here and print something. And only 2 seconds later, we return to this await delay and we carry on with continuation. So you can see that, hey, if we see the output, you can see that we started some nesting here and then the side job was introduced and then we carried on after sleeping for 2 seconds, okay? So this is the whole point of async and await machinery, that we can actually unblock the operating system level thread and run multiple tasks when one is waiting for the other, etc. So this is how we start. So asynchronous code is all about not blocking the operating system level thread. But we can actually block something else to make it a little better. Async in C# is generally implemented as coroutine compiler level transformation, which is this async keyword, which compiles the code to this magic long code, which I've shown you at the very first slide of this presentation, okay? So this is the coroutine compiler transformation. Then second, it uses the service locator for promise orchestration. The service locator here is basically the synchronization context. So it uses this globally accessible state to orchestrate how the tasks are executed one after another, okay? And the last part about async is it statically bounds promise factories. So whenever you actually hard code the type you return from your function, so whenever you hard code the task type, it knows which factory to use to create a task, to create these coroutines for you. So this is why it's statically bound, because it's hard coded in the source code and you cannot change it at all. So we are going to fix these two things. First, we are going to do is we will replace the coroutines And instead of blocking the operating system level thread, we are going to block using fibers. So let me uncomment the code, rerun the code, see if it works properly, because it may not work because I have a zoom under the hood and sometimes it slows things down. So what we are going to do now is let's enter this fiber async. So fiber, what is a fiber is basically a user level thread which sits on top on the operating system level thread. So what we are doing is instead of blocking the whole operating system level thread, what we would like to do is we would like to have like multiple threads running inside one thread. So what we need to do is we need to have a bit of bookkeeping, which I won't get into details. But what we are doing is we are creating 3 fibers running on this one operating system level thread. The first fiber with ID 0 is like the general scheduling fiber. And then we have fiber ID 1, which is run internal, and then fiber ID 2, which is a side job. Some more bookkeeping code, but ultimately what we do is notice that we create a task from task.delay, and then we call a magic wait method. And this is the truly magic wait you always wanted to have if you ever integrated asynchronous code with synchronous one. So what happens is we do not have any async here. We do not have any await here. We just code something like .wait, only this time it's magic wait, but notice in the output of this application that this side job was introduced in between. So we do not block the operating system level thread, but we block the user land thread, and then we can use another user land thread to execute this side job on the side while the operating system level thread is not blocked. So this is the truly magic wait we all wanted to have, and this is a pure C# doing all this magic, this trickery. So we can fix at least this coroutine compiler level transformation because there is no async await in this code at all, but we get all the benefits of async and await. Another thing which we would like to do is we would like to get rid of this static bound promise factories. Let me just compile the code properly, and it requires a couple things to be recompiled under the hood because it's a lot of machinery, which I'm not showing to you. What we are now trying to do is we introduce some kind of higher kinded type. So we are introducing some sort of generic. So instead of now returning the task at all, or actually conceptually having the task type, what we do instead is we have generic methods, and these generic methods, what they do is they use this type T to do the coroutine orchestration and everything else under the hood. So you can see that now I call the delay of T for 2 seconds. And this delay is basically creating some type T and then calling timer, etc., and doing some magic with monads and higher counted types. So you can see the important thing is it works. It did interject the side job while we were waiting. But the bigger thing here is I have multiple builders here. I can now replace the asynchronous builder with synchronous identity builder without changing the business logic at all under the hood. Notice nothing changes here. The only thing which changes is this T type, which is being used to execute this code. And you can see by changing this T, this time the side job is introduced or is executed at the very end. And because this is a generic type, this thing can be highly optimized because we can use structures, we can use the devirtualization tricks to actually make this allocate even less. So you can see that, okay, this code looks much worse, but on the other hand, we could have some FODI rewriting this code, or we could have just the C# compiler doing this for us, and we would be able to control the whole asynchronous invocation from the very top just by using the generic parameter. So this is how we can improve these things. And just to summarize the talk we just had, know your synchronization context and do not abuse it. It's very easy to get deadlocks with this code. Always have async task methods, never use async void. Always have async all the way up, configure await false all the way down, await all the tasks you have. And generally, you need to transform your code to this whole mindset. Otherwise, it may be super easy, super simple to break it, to deadlock it. That would be it when it comes to summary. And now it's time for Q&A. So let me open a chat and let's see if there are questions somewhere here. Let me just find the chat. Okay. Okay.
So now there are no questions, but guys, you can write them.
Oh, okay. So feel free to post questions. Feel free to speak up if you do have any questions. I can answer.
Yes, if you want to speak up, you can push raise hand.
Okay.
Hello. Thank you.
Yep. Go ahead.
Thank you for interesting presentation. You cover a lot of interesting cases about async CPU consumption method. Do you have some advice or best practice for input-output based async method or async programming?
That's a very good question about like CPU bound and IO bound methods. Generally, you should never use async await with CPU bound methods. That is because it's not for this. Like for the CPU tasks or heavy CPU tasks, you should always go with other things, because the whole point of async is to unblock the operating system level thread when you are doing nothing and we are just waiting for something to happen. So whenever you do, so the async and await should be used with IO operations only, because only then you can wait for something and you can just, you can do something else in the meantime. So advices here, or like pieces of advice, or what we should be doing is, generally, do not overuse the async and await for everything. Do not use await like for all the things you have. It's not for all the like background jobs, all the concurrency, etc., etc. Just use it for the IO. Otherwise, you risk you just increase the memory usage and the allocation cost, etc., without benefits, without the main benefit of the async and await. So that would be my piece of advice. Does it answer your question?
Thank you.
Cool. There is a question in the chat. Do you have an experience with TPO data flow library? If yes, can you say a few words about pros and cons of using it? Data flow, I do not think I recall this library. If this is something different than TPO, and I do believe it is different because it said TPO data flow here, then I don't know about that. So sorry, I don't have any recommendations regarding that. Any other questions? Cool. If there are there are questions. What are the benefits, potential problems of omitting async await in methods which consist of only one line, like public task do async, which calls operation async? That is a very good question, actually. There is a GitHub page. I don't recall the name, but if you type Google something like async await best practices, Microsoft GitHub, something like this, you'll find a big article. And the question which we need to answer is, if we do have a task, an async enabled method, which for instance just does await task delay, something like this, okay? Should we await this method? Should we write this method as await task delay? Or maybe we should just return the task we get from the task delay. So we should return task delay and do not do async in this method signature. And the current Microsoft recommendation is go with async. And that is because if you go with returning the task directly, straightforwardly, you change the exception behavior. You change how your application handles exceptions and how your application captures these exceptions, because the async rewrites your code and changes these nifty details. So general recommendation is go with async, but remember that it's not free. Like if you want to write high performant code, you may want to get rid of async and just return tasks as much as possible. But if you want to be safe, then it's easier to go with async. That's like a rule of thumb. And I encourage you to take a look at my internals of async talk, which you can find on YouTube, where I explain all the details of this coroutine transformation, so you can figure out why these exceptions, why they change, how they work, etc., etc. If this does not answer your question fully, please type in the chat, and I will now move on to other questions. Do you have any best practices when it's good to use tasks? Just like I mentioned, that depends in which context you want to use tasks, because tasks is with TPL world, so the old tasks from like 10 years ago, and tasks are used with async and await. And the general rule is, if you have CPU bound operation, like you want to actually calculate something, then you go with TPL and you do not use async await at all. You just go with TPL. Obviously, you may want to use await at the very top or somewhere, but generally you go with the TPL world. But if you do IO bound operations, so you read from files, write to network socket, access directories, etc., then you go with async and await, and then you actually get this performance boost because you unblock the operating system level thread. So this is what you should be doing. This is how you should be using tasks. So for CPU bound operations, go with TPL. For IO bound operations, go with async and await. And again, if this does not cover all the things you'd like to ask, feel free to type in the chat. And the other question is, could you recommend any async synchronization primitives, or it should better be avoided? That's a very good question, because I told you that you cannot use the old primitives, the synchronous mutexes, etc., with async. So now the question is, hey, what do we use? And the answer is, I believe I can recommend the Async X library, which is written by Stephen Cleary. And it does have a couple of synchronization primitives for asynchronous code. So if you do need to synchronize your thing inside async and await context, take a look at this library. I think I will post it in the chat. Sorry, it's not this, it's this. It's called Async X. I believe that's the name, and you can find it on GitHub, and it should cover this use case. That's all questions I have. Are there any other questions you'd like to ask? Okay, I don't see any questions. Feel free to type in the chat. And in the meantime, we'll start wrapping this talk a bit. So a couple references for you. If you would like to learn more about the mechanism I shown you, couple books for you, going like from the highest low-level code to lowest low-level code. So you start with CLR via C#. Even though it's for .NET Framework, it still covers a lot. And then you actually need to start understanding things in the operating system itself. So Windows via C++ is a user-land explanation of the Windows platform. So it's a pretty good place to do. You don't need to understand C++. You can skip the codes, but you just understand the mechanism because they are well explained over there. Then we probably should move on to the kernel programming. So Windows internals, developing drivers, etc. If you would like to see all these things under the hood, how they work, great, fantastic books by Mario Hewart, Advanced Windows Debugging, Advanced .NET Debugging. Recommend taking a look at them. There are also, I believe, plural site courses with the same titles. So if you don't want to read, you can just watch the videos. When it comes to a couple other things, there is a very nice book called Book of the Runtime. It's a GitHub book, a book available on GitHub, which explains all the things of the .NET Core platform currently. If you would like to read more about the things I covered today, I invite you to take a look at my blog. So a couple links for you where I show a couple other async, await, and threading tricks. And if you would like to read about these things on the internet, but outside of my blog, there are a couple more links for you to read about task internals and task completion source, etc., etc. And I highly encourage you to take a look at what Stephen Cleary writes, because Stephen Cleary is like a god of the asynchronous programming. So you can find him on Stack Overflow answering all these questions, and you can find his blog where he explains plenty of these interesting details. So if you just want to have a good read and understand async and await, Stephen Cleary is the go-to person, and his blog is the way to go. That would be it when it comes to the references. There's yet another question on the chat. Is it the best choice to use async and await while getting and updating databases? That's a very good question. And I do believe the answer is yes. That's the whole point of async and await, because calling the database is by definition an IO operation. You go to the database, you read some data. So this is an IO operation and you need to wait for your database to do the processing. So in that case, using await is a way to go, because you can unblock your operating system level thread and you can improve the performance. This was one of actually the biggest performance gains in the .NET Framework and .NET Core. Well, all these IO operations like talking to databases or talking to sockets were moved to async and were highly optimized. So I do believe, yes, generally this is a very good example of using async and await. And I don't see any other questions? And I don't see any hands striking here, so no one wants to ask me anything. So having said all of that, I think it's time to call it a day on my side. So thank you for attending this talk. Hope you enjoyed it. Hope you liked it. Feel free to take a look at my blog again, at the videos, and have a great evening. Thank you.
Thank you. Thank you so much for being with us, for your time. And thank you guys for attending this webinar. And you can join our Facebook page. We post there all of the future events. So I will be very happy to see you again, all of you. Thank you so much.